Good afternoon, everyone. Welcome. My name is Dr. Philip Phillips, and I'm the Associate Dean of the University Honors College here at MTSU. This is our penultimate class of the semester. Our class this week and next week are devoted to student presentations. And Dean Weil and I have selected 4 of your peers to give presentations, 2 today and 2 next Monday. We've selected people who've done outstanding work, and we've tried to select topics from a variety of disciplines. So this week and next week you'll learn about some very interesting projects, and you'll also learn some things about the process that your peers went through in getting to this point. So the roll sheet is going around. Make sure that you sign that, and if you have not picked up your paper, the remaining papers are here at the front. At this time, I'd like to ask Dr. John Weil to come and introduce our speakers.
I think we're going to do these separately. We purposely have chosen topics that are different, both today and the 2 that we're going to hear next week. So we're going to start with Grayson Dubois. Grayson is majoring, you can probably guess, in computer science with a minor in math. He is part of the mobile development team at MTSU that works on the MTSU mobile application. This summer he worked with Hospital Corporation of America developing a mobile application to monitor data flow through its network of 169 hospitals, and already has been offered a job to work with them in May. He spent a previous summer at Oak Ridge National Laboratory writing simulations of bacterial colonies, for which he earned a Goldwater Honorable Mention. And his thesis deals with augmenting a software toolkit designed to simulate cognitive tasks by emulating human working memory systems. He's going to have to explain it to you, so I'll introduce him now.
All right, guys. Thank you guys for coming out today. I'm very excited to share what I've been working on for the past year with you guys. First off, how many of you guys are currently working on Thesis right now? We got a few. Anybody who's already finished? All right, we got a couple as well. Congratulations. And then for the rest of you guys, I hope you're really excited. It's really, it's a very fun process, and you definitely learn a lot through it. So, like they said, my research dealt with basically working on a software toolkit that my mentor had made previously, which allows cognitive scientists and psychologists to write simulations of cognitive tasks based on human working memory. And so I'm basically going to describe to you a little bit of background, how that works, and how I kind of helped to push that project forward. So I hope the title doesn't terrify you. I know it's very intimidating. So a little bit of background. There's an area of artificial intelligence that deals with thinking humanly, or what they would say. And that's basically coming up with computer systems that work similar to how the human brain works. These are usually implemented using something that they call artificial neural networks. And there are a number of reasons, 2 which I'll go over here, that these are very useful tools. 2 of them are, the first reason this is useful is because it allows us to basically test out theories of how we think the brain works by writing computer programs that follow the same steps that we, if anyone has a theory about a cognitive process, they basically can write a computer program and see if it behaves similar to how a human would. And this is a good way to test that. Another reason that this is useful is because these neural networks can solve engineering problems that other engineering solutions cannot or do not perform as well. For example, elevator scheduling is usually trained on a neural network. There's basically a neural network inside the elevators which monitor foot traffic and figure out how to schedule what floor it needs to go to, when, that kind of thing. Also, another common example is credit card readers. Every time you or I scans our credit card, that information gets sent through a neural network, which has been trained with millions of other card scans and card swipes to basically detect whether or not somebody has stolen your card and is committing credit card fraud. So another piece of basically the focus within this area that our research dealt with was working memory. Our computer system, our neural network, was based off of a model of human working memory. Now, for those of you who aren't familiar with working memory, it's basically just the workbench of your brain. Every time you do any sort of simple task and you need to hold on to a little bit of vital information, that is being held in your working memory. And then as soon as you're done with it, it goes away. For example, if you woke up in the morning, you want to make yourself some pancakes. You get out all your ingredients and everything, but you're not quite sure exactly how many teaspoons of salt, say, you need to put in. So you read your recipe book, and it says you need 4 teaspoons of salt. Now, that information is being held in your working memory as you're putting the salt into your mixture. And as soon as you're done with that, it goes away. You forget it. You don't remember exactly how many teaspoons of salt you need to put in there unless you memorize the recipe. So for example, let's say you were doing that. You're putting your salt in your mixture. Somebody comes up and talks to you. You have a conversation with them and you come back and you're like, oh no, I don't remember how many teaspoons of salt I'm supposed to put in. That's because as soon as the information that your working memory is holding on to is no longer relevant, it discards it. So what you have to do then is look it up, figure out that you're supposed to put in 4 teaspoons, and then just play it safe, put 4 more teaspoons in, and you have salty pancakes. But that's basically how the working memory system works. It holds on to information that it thinks is valuable for the task that you're doing, and it learns basically what type of information is valuable based on whether or not it yields a reward. For example, you probably won't get a reward for eating those pancakes because they were kind of salty. But if they were delicious pancakes, it would remember, okay, the exact number of teaspoons that we need to put in this recipe is important to hold on to. So it learns over time what is valuable information to hold in your working memory. And this is the working memory toolkit that my mentor built was basically built using a neural network that does this exact same type of thing. The problem, however, was that, as you know, computers don't represent regular concepts like a teaspoon or an egg or the color red like the way that you and I do it. We consciously remember and think of concepts symbolically. Like, for example, if I say triangle, you probably now have a picture of a triangle in your head because that's how your conscious brain represents those concepts. But as we know, computers represent these in what we call a distributed formalism, like a list of numbers, a list of ones and zeros. And the problem was that any type of researcher or cognitive scientist that wanted to make a simulation or anything using this toolkit, they had to manually handwrite the lists of ones and zeros, the representations that the computer had to understand for every single concept that they wanted to use in the simulation. This is a very, very, very simple example of what that would be like. Say you had to come up with a schema for representing a colored object. You basically just have a list of numbers, and the first 4 represent what shape you want to represent. The last 4 represent what color. And therefore, using this schema, you would come up with this vector with just ones filled in for, I guess, the concepts that you want to turn on, the ones that you want to be active. And that is how you would represent a red ball or a red circle using this. Now, that's a very simplified version of kind of the handwritten process that anybody had to go through in order to make a simulation. As you can tell, that is very, very tedious and very difficult, especially if you don't know how an artificial neural network works. So my part of this project was to abstract away this detail, this process, to make sure that anyone who wanted to make a cognitive task using the toolkit doesn't have to worry about this. So what we did is we used a method of representation called holographic reduced representation. And basically what that is, it's a big fancy name for something that's not as scary as it sounds. You have a list of decimal numbers chosen from a uniform distribution between -1 and +1. So you have this vector, this list of small decimal values, and you just randomly generate it, and you literally, all you do is assign it to whatever concept that you want to represent. Say if you wanted to represent a ball in the computer, it knows now that if it says this list of numbers, that represents ball. And if we ask it for a ball, it will use this list of numbers, and so on. What makes these so powerful is the types of operations that you can do. Basically, there's a bunch of math that you can do called circular convolution, circular correlation. We won't go into that. But basically, mathematically, you can combine separate concepts into a single concept that is unique using some of the operations that it gives you. For example, if you have a unique concept for the color red, you have a unique concept for a ball, you can use a convolution operation to basically combine those into the complex concept red ball. So mathematically speaking, all that you need to worry about is now you have two of these that were different. They have been mathematically combined into one single vector that has the information from both, but is still the same length. That's why it's holographic, is because you have multiple layers of information in a single vector, and it's reduced because it doesn't grow at all. It reduces that information into a single vector of the same size. Now, that was probably the hardest and most confusing part of it that we'll cover. Basically, what I did was, here's an example of the original toolkit and the augmented toolkit that I built. Basically, all of the last two slides, all of the work that had to be done to do all of those confusing processes had to be written and hand done by the user every single time, and that's what these green hexagons are. And those are all the things that have to be done before a researcher can even start to write their cognitive task. So what I did was I wrote an HRR engine, which just basically every time you hand a concept to the toolkit, you say, hey, you're looking at a ball. It would hand that concept, the ball, to the engine, which automatically generates all of those representations and handles everything with those. And then the toolkit can do the artificial neural network can then learn using those representations and do the working memory tasks, and then basically tell the user exactly, hey, okay, you gave me all of these things to remember. I'm telling you this is the most valuable thing to remember right now. So that's kind of an abstract form of how it works. The biggest point is that beforehand, any user had to manually write all of these different functions. And basically, after my project, all of that is abstracted away. They don't have to worry about it. This increases the ease of use and actually opens up doors to other possibilities. So we know that it works because we did a couple of simple tests. The first we did was just a very, very simple colors task, which you can think of as, say, I come up to someone and I show them 7 cards, and each card just has a different color on it. And at the very beginning, I think to myself, I want them to remember the color red. And at the very end, you ask, what color do you remember? And if they say green, you say, no, let's do it again. And so you keep doing that again and again until they say, oh, red. And at first they don't know. They're just picking randomly. And you say, congratulations, you won. Here's a gummy bear or something. And you continue doing that until they finally realize, wait a second, every time that you show me the color red and I say red, or every time I tell you the color red, you give me a gummy bear, there must be something important about red. I'm going to remember that. So that's basically how that works. And it usually takes about 8,000 trials to get within a 100% success rate. Now, that is a lot for such a simple task, but it's not a trivial task. If you think about it, if I came up to one of you guys and just started like looking at you and showing, like putting down cards and saying, which color do you remember? It'd probably take you guys a while to figure out what I even wanted. So also, that's how many trials it took to get within a 100% success rate. I think it took about half as many to get within 90 to 95. The other task was something that is more well known in cognitive science, cognitive psychology, called the Wisconsin card sort task. And basically how that works is you have cards that have shapes, colors, and a different number of those colored shapes. And what it is you basically are at the very beginning, a rule is picked, say triangle. And then the user or the agent, what we would call it, has to draw a random card that has, say, 3 yellow diamonds and say, okay, does this card match the rule? Now originally, at the beginning, the agent does not know the rule, so it's just choosing randomly. I think it matches the rule. No, wrong. So it picks up another card and says, does this one match the rule? And say if it was 4 blue triangles, say, no, it doesn't. That is correct. It does not match the rule. And it keeps going through this step until it actually chooses the correct, categorizes the correct card based on the rule. Like, for example, once it realizes that the rule is triangle, anything that has a triangle in it, it's going to put in the correct pile, and everything else that it sees, it's going to put in the discard pile. At which point you switch the rule, and you have them learn all over again. And I can imagine if anybody went through this task, if any person went through this task, it would probably be very annoying at some point, because you'd have the success of, yeah, I know what's going on. Every triangle I put here, everything else I put here, and all of a sudden you start getting things wrong because they changed the rule. So it took about 35 to 4,200,000 trials to learn a new rule. But at the same time, that also kind of makes sense and is kind of okay because this is it's not nearly as advanced as the human brain is. But we do see that it does actually work and it does learn. So things that we achieved during this project, we greatly improved the ease of use. I know you guys probably agree with me that everything that had to do with those representations was just horrible, and nobody wants to think about that. So we made sure that that was abstracted away. We made sure that if you want to introduce new concepts, like a new card with different types of colors or anything, you don't have to change anything, because beforehand, the user would have to go, okay, well now my schema for how these representations are built doesn't work. I have to rebuild everything. We don't have to worry about that anymore because the HRR engine automates the whole process. And using HRRs, actually we found out it opens up the possibilities to things like chunking similar concepts in memory, and then things that you learn from doing one task will actually help you in learning another task, which was not possible before. And probably the most important, the most significant thing that we accomplished with this project is showing proof that you can use HRRs to learn using neural networks, which had not actually been done before. And so that opens up the possibility in the field of AI and artificial neural networks to so many other possible research projects. So with that, if there's any questions, do we take care of questions now or at the end?
You
go ahead and take questions now.
Okay. Yes.
Who was your project mentor?
He was Dr. Joshua Phillips from the computer science department. Yes.
You had mentioned that this sort of thing opened up a lot of doors for artificial intelligence. So if it can be used to learn, is this just for working memory, or could it be used to build on? Could you build further from there with the HRRs and other tools you found here? Absolutely, yeah.
This specific project was working with working memory, but it just so happens that this is a new, basically a new approach to try to tackle this problem, and it shows that you can use this with any neural network using the specific algorithm that we used was called TD learning. You can use these HRRs for doing that kind of learning in any type of neural network. This specific project dealt with working memory, but you can do it with any other neural network application that you could think of.
Yes. So this one might seem slightly silly, but it's something that I thought about after watching the second Avengers movie. How close does that mean we are to something like Ultron?
Very, very, very far. Very far. So, because
this would be a building block toward that, though.
it could be a building block, yes. But it's a very, very tiny, tiny building block in a giant Lego fortress, basically. Because it's still it's the amount of math calculations that have to happen in order for this to work is very slow. So it's not even kind of as efficient as the human brain at all. And then there are so many other processes that the brain does. Like think, right now it's just regulating temperature and like for the body temperature and your breathing and everything else that is automatically happening in your body that you don't consciously think about. So we are so far away from that. Yes. Yes, and then I'll get you to take it.
I was kind of wondering, because when breaking this down, it sort of seems like this is very similar to those things you can buy at Walmart that are like 20 questions, and the difference being that, that's sort of eliminating a lot of possibilities. What would you say is like the major difference between something that works like that and what you have here?
What do you mean? So 20 questions, is that like
That's like where you come up with something in your head, and then it asks a series of questions, and by the end of it, it comes up with the answer, no matter what it is.
Oh, gotcha. Well, that, I don't know. I think it could possibly be used for similar type things. That could also, like, I can imagine that being a problem or something that could be solved with an artificial intelligence approach, like just taking answers that you've heard of before and coming up with a conclusion based off of that. But this specific project might be a little bit different because it's working on holding specific task-relevant information. So, say you've got, there are so many applications, and normally what computers do is they have this giant database of information that it can randomly search through and pull from. But this kind of is building a component that kind of gives a focus on, okay, we've got all this other information. It'd be super slow to look through all of that. So we're just going to say that this is what we think is really important to focus on. So it's kind of a little bit different, I think. It has a bit different focus than what a 20 questions thing might do. I don't know if that answered your question.
Yeah, it's in the brain.
Okay. You have a question?
Yeah. Did you work with a psychologist for your project, or is psychology something that has become incorporated with computer science?
So I didn't actually. Dr. Joshua Phillips basically had all the knowledge and literature beforehand that we needed to accomplish the project. But we are kind of in this area of computer science and artificial intelligence that overlaps a lot with cognitive science. So there are a lot of like psychological aspects of it that we're actually able to bring into computer science. There's this giant overlap, and we're kind of within that overlap in the scope of this project. So like there's probably some cognitive scientists that are primarily psychologists, but can also do some computer science and coding for this kind of thing. And then we're kind of the opposite, computer scientists that apply our software knowledge to solving a cognitive science problem or question. Yes.
How much does you mentioned applications for this. How much would something like this, like as an HRR engine, either for working memory or something else, how much do you think that speeds up, say, IBM's Watson or Deep Blue, one of these programs?
That's a good question. Yeah, that's a good question. So it's actually, so the examples of HRRs that I showed, this one just has 6 elements, 6 values. That really doesn't work for larger numbers of concepts. We found out that you kind of have to use vectors that have like 256 or even 1,024 elements in it. And if you're going through a massive list of concepts and comparing every single one, that's very, very slow. Yeah, so knowing that IBM is very, very good at what they are doing with Watson and their AI platform, that probably would actually slow it down. But it is very good for this type of learning approach, primarily because it automates the encoding. So I don't know about time, but we should probably move over to Mitchell. Thank you guys very much.